Okay, so good morning. And so how about the exercises? Did you make it? Okay, so before going to for the parallelization of the 1D case, so I just briefly overview the first small one for the three domain cases. Okay, so this is a slide which I showed yesterday at the last part of the MBI2. So afternoon yesterday, I described the distributed local data structure for parallel computations. So actually, so you use that, so everything is easy, and if proper data structure is defined. And the values at boundary points are copied into sending buffers, doing the send and receive. And the values at external points are updated through receiving buffers. So this is a problem. So yesterday afternoon, I showed 64 meshes in 4 uniform domain cases. But in this case, we have 3 a little bit unstructured partitions. Okay, and so this is a local mesh ID in red letters, and the blue parts are internal points, and so white parts are so-called external points. So what we are expecting you is complete this local data structure for 3 separated meshes. Okay. As for the first 2 parts, naive B dot and the naive B, it's already done. And what you have to do is complete the node part and import index items and export index items. So as was the case of the node, so it's easy. So because we have already specified the number of internal nodes in each part, and also external nodes are also specified. So it's not so difficult. And the problem is how to define the these communication table. Okay. And the procedure is we need to specify the number of the internal and external points, and we do external points. So where do external points come from? So it's easier and to construct the input index and the input items. And please consider the sequence of naive P. Then check destinations of boundary points. It's a little bit complicated and more difficult. Okay, and you can get the answer at this directory. So if you go to the PFM answer and the T2. So T1, you can find the first exercise in yesterday morning. Okay, and you can find this one in the neighbor directory. In this directory, so you can find resulting files and also this shell script. Okay, so in this case, you are running 3 processes. Okay, so this is about the external point. Okay, so now we are focusing on the process 0, and you can see we have 5 external points, and you can easily find where they are they do they come from. Okay, for example, this one, 9 and 10 is originally it's a 9 and 10 in the global numbering, so they are from this one. Okay, and this 11 to 13 is from process 2. Okay, so like this way, so you can write the information, and you can see node number is already defined. So we have totally 13 nodes in this number 0 process, and we have 8 internal points. Okay, and we have totally 5 input items, and so first 2 are from this number 1 neighbor, and the latter 3 are from the number 2 second neighbors. And you can see, so numbering is in like this way. Okay? And this is the case of the process 1. And we can do this way. And yeah, same things can be continued for the process 2. But in this case, you need to be careful, okay? Because so you can see, so in the process 0, 10 to 12 come from process 0, okay? And so 13 to 15 come from process 1, okay? But you can see, so the sequence of the neighbors are 1, 0, okay? So process 1 and process 0. So in that case, so you need to configure the import items in this sequence, okay? And so, okay, so yeah, you can see. So here we have 3 from number 1 neighbor. So in this case, number 1 neighbor is process 1, okay? And the second neighbor is process 0, okay? And we are accepting 3 external points from neighbors. So therefore, the import index is 3, and 3 plus 3 is equal to 6. But you see, the sequence of the import items are 13, 14, 15 first. Then 10, 11, 12. Okay, so you should be very careful about that. Okay, so next part is so where boundary points go to. Okay, so this is a little bit complicated, but so in the case of the process 0, so you can see the neighbors are process 1 and process 2. So therefore, so in this case, this is a process 1, and these are the external nodes, and they are come from process 0. And this is a process 2, and these external points are come from process 0. So we just combine these information to get information about the boundary points. Okay. So in this case, we are sending the 3 boundary points to the process 1, 4 and 5 and 8. And also we are sending the 3 boundary points, 6 and 7 and 8 to this process 2. Okay, so totally we have a 6 boundary point. And also you need to be careful about the sequence of the sending and receiving, because so basically they are receiving in the sequence of the local number, so 9, 10, 11. So that means, so we need to send that send the boundary point in that sequence, number 4 and number 5 and number 8. Okay, so yeah, you need to careful about so the sequence of the sending and the sequence of the receiving. Okay, and you need to make sure that so paper data is received in the destination. Okay, because so if you send this information to this one, so it's wrong. Okay, so you need to send this information to this number 10. Okay. Okay, so this is how we define the local data. Okay, so this is the process 1, and this is the process 2. Okay, and so number 0 is the first neighbor of this process 1, and so this guy is receiving number 9 and 10 and 11 like this way. And this number, the second neighbor is so number 0, and 10 and 11 and 12, or this one. So these are received. Okay. So therefore, so you need to specify the boundary nodes, and so 4 and 5 and 8 are going to 9 and 10 and 11 in this process 1, and 6 and 7 and 8, so they are going to the process 2 and received as a 10 and 11, and 12. Okay. Yeah, you need to continue. So repeat this kind of processes for other partitions. Okay. I skipped the details, but I hope you understand how should we do that. And for the last part, process 2, and you can see the sequence of the, so this neighbors is starting from 1. Okay. Then we also consider that for the export items. Okay. We are sending the, so this one, number 1 to the number 1 process first. Then we send the, so these values to the process 0. Okay. So 3, 6, 9, and 1, 2, 3. Okay. Okay, so this is a results. So if you run the code, and so you can see, so this is yeah, these are the local ID of the external mesh. So this doesn't appear on the result, but you can get so which values are received. And this 6 and 7 and 8 are so this small one, global node ID, and you can, if it appears on the list, this is correct. Okay, so I'll show you the examples, and so yeah, of course you can do this. Okay, oh, it's already done, but so I just run again. Okay. Okay, it's finished. And if you type the cat that list, test that list, and you can see, so, oops. This one, so number 1 is receiving, okay, so you can check this black number, 4, 5, 8, and 13, 18, 23. Okay, so you can see, so this is surely so received here. Okay. Yeah, I don't repeat the same process for the other part, but so you can so just confirm that by running the code. Okay. So any questions for this part? Okay, so if not, so let's go to the this big exercise. Okay. It's a parallelization of the 1D code. Okay. And this is the problem definition, and you are already familiar with this. And this is the finite element code. And this is the analytical solution. And so the second exercise is learning the, so developing the code, and also validate the results. Okay. So using the generalized communication table, which I mentioned yesterday afternoon. And so if you log into the system, so you can get the sample code from this S2R minus F dot or minus C dot. Okay. And you can copy to your so directive, not directive, your directory, sorry. Okay. And so you can compile, okay? And in the case of the program, so we have actually two codes, 1D.F and C, and 1D.F and C. And so mainly we are focusing on this 1D.f, but because we have two types of the source code, so specify the name of the executable file by this minus small o, okay? 1D and 1D2. Okay. Okay, so before, so yeah, okay, so you can do this later, okay, by compiling this. Okay. But anyway, so please do the first one. Probably it's better to do this now, okay? And copy your files and please copy the please compile. Okay. Okay. Here I'll go to the C directory and it's mpy I and s2 ref and mpif cc ccpx n ground minus k fast 1d.c minus small o 1d. Oops. Oh, I need to module. Okay. And also you can compile the 1d.c to the 1d.f. Okay. And please make sure so 1d is created. Okay. So next page shows input data. It's a control data, and it's same as for the PC version. But you need to make a very large number of elements. So in this case, it shows 1 million of nodes, elements. But so second line, third line, and fourth line okay. And you can see, so if you remember the features of the conjugate gradient method in the 1D case, so you need 1 million iterations if you have 1 million of elements. But in this case, we just keep the number of the iteration number just 100. Okay, this means so it stops the computations, although it's not converged. But so it takes a long time to take the computation with 1 million cases. If you use many nodes, it's okay. But if you try to do that with a single node, it cannot finish within 15 minutes. So which is the limit of our resource group. So therefore, we just define the small number of the iterations and compare the result. Okay. And of course, we need to check we have a same result even if we change the number of nodes. Okay, so I'll show you that type of the examples in the later part. Okay, so any questions or problems or compiling? And this is a 348.sh and it's 8 nodes and 384 cores. Okay. And we have other type of the shell script in this directory. And you can change the number of processes as I mentioned before. Okay, so let's do the example. Okay. So in this case, we try the 1,000 elements and 1,000 iterations. So this means, so it's not converged, okay? But so we can compare the single CPU case or single core case, and I think the multiple core case, so 384 process case, okay? Okay, so please open the, so input that, and you should modify that like this way. So number should be 10,000, and iteration number is 1,000, okay? And you can open the G1 go1.sh, go1.sh. Oops. Just a moment. Sorry, I haven't. Okay, sorry. So I think it's already in the Fortran part, but it's not included in the C part. I'm very sorry about that. So could you copy the file again? Just a moment. CVF S2. Okay, now it's go.sh, go, yes, okay. Okay, please copy the file again. For this, please go back to the previous page. And please do this copy for the C users. And it's already compiled, and so you don't need to repeat this. So you just copy the file and open the archive. So I'm very sorry. So please repeat this part. Okay. And you have go1.sh, and please modify this so lecture 7.0 and GT17. Okay. And go2.sh. Also, you need to do this lecture 7.0 and GT17. Okay. And so this one is a single CPU or single core. And this one is using 8 nodes and 384 cores. And the output is a go1.list here, and this one is a go2.list here. Okay. Okay. And please run the both program. Okay. Script go1.sh and go2.sh. Okay. Okay, so please copy your file to your directory and just open. And yeah, please just go into this modifying the shell script on this page 13 and page 14. Okay. Oops, これです。So this one is Go 1. Sorry about that. Okay, so this is a go1.sh, and this is a go2.sh. So anyway, so please change this resource group to lecture 7.0, and this one is GT17. Then you can run the file. And if your works were finished, so you can compare the go2.list and go1.list. Okay, and so actually it's almost converged. But anyway, so you can compare the result, and so if you go to the list here, this is the go1.list. And also you can write a go2.list. Okay. Okay. So this one is a result at the ending point. Okay. And if you compare these two results, so they are same, and they provide the result. Okay. Even if you apply the parallel computing. Okay. So yeah, please make sure about this. Why we have these two values here? But I think this should be 1. Okay. Okay, and so this result shows at this point. Okay. And so you can see the single CPU case and also the 384 core case. So they provide the same answer. Okay. And also, if you like to confirm that result on your PC, so you can do this. Okay. So this is a result for the converged case. Okay. And this is a correct answer. Okay. And you can see both of the analytical solution and so finite element solution shows 50 millions. Okay. And if you run 1,000 iterations, so this is a iteration, and it's not converged yet. Okay. But you can see it's same as the result of the parallel computation. Okay. So that you can validate the answers for the parallel and the serial computations. Okay. Does it make sense? Any questions for this part? Okay, so let's go to the inside of the computations. Okay, and this is the procedures and reading the control file and entire element number, etc., and creating distributed local data in the program, and assembling local and global matrices for linear solvers, and solving linear equations by conjugate gradient. So basically, not so different from those of the original code, but the problem is we need a lot of procedures for preparing the parallel distributed data. Okay. so starting from the distributed local data structures, and I have already shown this before. Okay. So basically, so this is a node-based partitioning, and local data includes nodes originally assigned to the domain or EE or partition, and elements which include above nodes, and nodes which are included above elements and originally not assigned to the domain EE partitions. So we have three categories of nodes. Okay, one is the internal nodes, so it's they are originally assigned to this partition. External nodes are nodes originally not assigned to the domain, but so it's included in this overlapped element. And boundary nodes are part of the internal nodes and external nodes of other domain and processors, and communication tables. So this is a 2D case. So we have 25 nodes and 16 meshes. Okay, and it's divided into 4 parts. Okay, and these green meshes are so-called overlapped elements at the domain boundary. So this is a local data structure, and if you consider this process 0, so these are the internal points. And we have connected elements, and these green parts are overlapped elements. And so we have some external node. And if you have this type of local distributed mesh set, the matrix assembly can be done in totally parallel manner. So you don't need any communications. So in the later stage of this 1D case, I will show you the example. Okay, so this is a 1D case. 12 nodes, 11 elements, and 3 domains. So like this way. So I have shown this before many times. So this is based on the original global mesh ID. But so according to the description of the distributed local data, which I mentioned yesterday. So we start from the internal node. Then we number the external nodes. Okay. And the neighbors are sharing the overlapped meshes, and the numbers and ID of the neighbors should be specified. And also we need the information about the external points and the boundary points. Okay, so let's think about the 1D case. Okay. So you can see, so numbering is starting from 0 for the internal nodes. Then we number the external nodes here. And we are also applying the local numbering for each element. And we start from the elements which only include the internal nodes. Okay, then we go to the these boundary element or overlapped element. And you can easily specify the external nodes, which is framed by these orange thick lines, and also these green ones. So green framed lines are the boundary nodes. So you can see, so boundary nodes are part of the internal nodes, but it's also external nodes in other domains. Okay. So in the case of the matrix vector multiply, we need the information from this so-called home ground, okay, to get the proper values. Okay, so this is a general numbering rule. Okay, so we have 3 parts. One is a number 0, and so this is another end. And so in this case, we have only one external node, respectively. But in the general case, inside the domains, so we have 2 external nodes. Okay, so the numbering of the nodes are like this way. So 0 to n minus 1 and n. Okay, and 0 to n minus 1 and n here. Okay, and in this case, 0 to n minus 1, n and n plus 1. Okay, so this is a general rule for numbering the local nodes. Okay, and this part, so this black part is a ID of the element. Okay. So by the way, we have a n plus 1 nodes and n elements for these two cases, and we have n plus 2 nodes and n plus 1 elements. Okay. And the numbering of the local elements are starting from 0 and n minus 2 here, and this one is n minus 1. So it's an overlapped element. So in the case of the other end, so it starts from 0 here and n minus 2, and this one is the n minus 1 element. So in this case, so it's a general case. So numbering is starts from 0 here, and this is n minus 2, and this is n minus 1, and this is n. So this is how we number the local nodes and local elements. So including the external nodes and also overlapped elements. Okay. And you can see, so if you have such local data structures, so at the time of the matrix assembly, so we can do the integration over each element in each process locally without any communications. So it's very convenient for the parallel computing, efficient parallel computing. And this type of the data structure is also good for the conjugate gradient method. And as I mentioned several times, so in the case of the this preconditioning and DAXP case, each computation is done for each component of the respectively, so independently. So therefore, if we have three divisions like this, so we can do the local computation on each process. So in the case of the dot product, so we can do this by MPI or reduce. And as for the matrix vector product, so we can utilize the communication table to get the information of the external point. Okay. I'll show you this. So how to do this in the 1D parallel case. Okay, so I have already shown this, and so you can see external nodes and boundary nodes. Okay. And this is a matrix vector product for the this three-diagonal matrix, and so yeah, we can construct these local matrix and so apply the local computations for the SPMV. Okay, because so these white part are all zero. Okay, so that means so we have no effect on the matrix vector multiply. And as long as we are doing the matrix vector multiply, so we need only these parts, so framed by these brown lines. Okay, and these matrices are constructed on the locally on the parallel computing. So these are enough. Okay, like this way. And if we consider the actual numbering like this, we need to have information from the external node. Okay, and so this rectangular matrix is multiplied to this vector, including external nodes. Then finally, so we get the information about the result for the internal node. So therefore, we need to import the most recent value of these external nodes. Okay. Okay, so I have already shown this. And in order to do this, so we use communication table. And this is a little bit complicated 2D case. And so, for example, this is a boundary node. So this number 2 is sending these information about boundary nodes, the neighbors, like this way. Okay. So in order to do this, so we just utilize a communication table, which I mentioned yesterday. Okay. And the first, we copy the value at the boundary point to the send buffer. Okay. And you can see, so this export item means ID of the boundary node. And this KK is not necessarily continuous, but this K is continuous. And we can copy the value at the boundary point at this continuous sending buffer. And after that, so we just go through the neighbors and specify the starting point and ending point and the message size like this way. And we are sending the values at the boundary point to the destination. Okay. So in the case of the external node, so we are receiving. Okay. So process 2 has so you can see, so these are 6 external nodes, and this part is receiving from process 3, and these 3 are receiving from this process 0. So in this case, you can see, so numbering is not continuous. Okay? So our current data structure can accept this type of the not continuous case. But generally speaking, so it's better for numbering in continuous in each neighbor. But currently, so you don't care about this. But anyway, so these are the information. And this is how we utilize the communication table for receiving. Okay? First, we just do the communications using this receiving buffer, okay, like this way. And after calling wait on, we copy the content of the receiving buffer into the external point. Okay, this KK is the ID of the external point, and in this case, we can allow the incontinuous numbering of the internal external nodes. Okay. Okay, so this is the very brief overview and review was communication at the boundary using communication table. Okay, so this is just a review. And any questions or comments? Okay. Okay, so we still have time. So we just make some small introduction about the program. Okay. So this is a first part of the 1D.C. And you can see, so compared to the original program, we have a lot of additional new variables and the new arrays. Okay, and these blue part are so corresponding these. Okay, excuse me. You can see, for example, this naive p dot my rank or naive p dot or so these are all so related to the communication. Okay, and also we need to specify the local value of the product and the binom to 0, 0, C1 0, and denom to 0. And we need to define the status and the request for the sending and receiving. Okay. And you can see size of the import index, export index, and the import item, export item are fixed because we have a fixed number of the neighbors and a very limited number of the external and boundary points. So we can specify the number of these beforehand. And you can see the size of the send buffer is equal to, and so the receive buffer size is 2. Okay, so this is a table of the variables and arrays. And NE is a number of the elements in each process, the local number. And NEG is a global number, so total number of the elements. It's an order of the elements or more, millions or more. So N and NP, N is the number of internal nodes, and NP is a total number of nodes, including external ones. So you can see NPMU. So these are not changed from the previous one. Okay. So next one is related to the vector and matrix. And please make sure size of the vector is NP. Okay, NP is including the external node. Okay, so please make sure about that. And the last one is about the parallel computing, and you can see the sizes of the neighbors or these parts are fixed. You can see the size is very small. Okay, and we just use these arrays. So this is a 1D case, but 3D case it's almost same. Okay, but in the case of the 3D, we have more neighbors and we have a larger size of the import item or export item. Longer receive buffer, send buffer. But basically, the structure is same. Okay? Okay, so I think it's a good point to stop. And so it's lunchtime now. Okay. Okay, so let's take a lunch break, and we start the afternoon session from 1. Okay, so from this page. Okay, thank you very much. Okay, so good afternoon. So let's start the afternoon session. Okay, so this morning I just briefly go over the variables and arrays for the parallel 1D program. So I just go into the details of this program. So this 1D code is still a single code without no external functions. Okay. So first of all, we are calling the MPI init, com size, and com rank like this way. And next part, we are reading the input dot. But you can see we are doing this just for the number 0 rank, okay? And we read the content of the input dot. And here, the first line, element number is a NEG. It's a global number of elements, okay?
So it's the order of the 1 million or something. Okay? And in the next part, we are using the MPI bcast and and sending individual data to other processes. Okay? So sometimes we do this because so in this case, the total number of the MPI processes is up to less than 600. So this is not a big number, but if we try to do this extend to 1,000 or 100,000, usually we do this way because if you try to access single file by 10,000 or 100,000 processes, sometimes it affects some performance of the file system. Okay, and so instead of that, so we just read that in a single process, then send that to the other process. So this is a very convenient way. And you can see the data size is not so big, and so broadcast to every other process is not so heavy for the communication. Okay, so in the case of the file applications, sometimes we do this way. Okay, so this is just a review for the interface of the MPI bcast. So this is sending the value to other processes, okay, from a single root. Okay. So in this case, we are sending the individual values, but so we can send that by arrays. Okay, so next part is constructing the local mesh size. Okay, and so NG is the number of the global nodes, total number of the nodes. Okay, because the NEG is the total number of the elements, so therefore, NG is equal to NEG plus 1. Okay. So next one is define the number of local nodes. So the value is n. Okay. And NG is equal to n equal NG by p dot. But NG is not necessarily divisible by p dot. And in that case, we just take some remainder here, nr. So nr is equal to ng minus n multiplied by p dot. Okay? And if it's not equal to 0. And if the my rank is smaller than nr, so in that case, so we just add one node to n. Okay? So we have a slight load imbalance, but it's not so significant if you have a large enough number of nodes for each process. Okay. Okay. So basically, so it's already SPMD. Okay. So n. So this large n could be different for each process. Okay, so next part is a number of local elements and the total number of nodes, including internal and external nodes. So if you think about this type of the internal processes, where we have neighbors in both sides. Okay, so in that case, total number of elements is equal to n minus 1 plus 2. So this means n plus 1. Okay, n plus 1 element. And NP is the total number of nodes, including the external node. So this it is n plus 2. Okay, so this is a general case. But we have some exceptions. Okay, so if my rank equals 0, we have a smaller number of nodes and elements. So this is also the case in another end of the point. Okay. So actually, so most of the process it for the 1D code is 1D parallel code is spent for such kind of the data generation. And we need to consider many exceptions. Okay, so please be careful about these type of the exceptions. Okay, so this one is a very rare case where we have only one process. So in that case, NE is equal to N minus 1 and NP is equal to N. So it's no communication and a single process case. And the next part is so we are allocating the arrays, and you can see so the size of the array is NP, not N. Okay, please be careful about that. Okay, so we just initialize these part, and so we have this isel node. Okay, so isel node is if we full node of each element. Okay, so generally speaking, so if you give this node ID, element ID, the first node is isel and the second node is isel plus 1. So this is a usual case. But if you consider the parallel data structures, including the overlapped elements, we have many exceptions. So this part provides such exceptions. Okay, like this way. Okay, so if the parallel case and my rank equals 0, so my rank equals 0 is this one. Okay, so in this case, so isel is equal n minus 1. So this one. Okay, so generally speaking, so in this case, this type of elements are different number, but so this one is a very special case, and you can see n minus 1 and n is two nodes for this exceptional node. In other cases, for this one, okay, for this one, we also consider the very special numbering for this overlapped element. Okay, so mesh ID is equal to NE minus 1 because NE is equal to N in this case. So therefore, so this is corresponding to this mesh. And you can see two nodes were N and 0. Okay, so this is also a very special case. And otherwise, so we need to consider the very special numbering for these two overlapped element. Okay, so first one is this one. Okay, first one is this one because NE is equal to N plus 1, so therefore NE minus 2 means N minus 1. Okay, and so two nodes are N and 0. Okay, and this last node, last element, these two nodes are N minus 1 and N plus 1, like this way. Okay, so we need to be careful about these exceptions. Okay, so K-mat is okay. So this is just so putting the plus minus 1. And the next one is about the connectivity. So first of all, we need to specify the index. Okay, so index means the number of non-zero components for each node. Because we have we need a very special treatment for the boundary nodes. So we have to be careful about that also. Okay. First of all, we just put the number of non-zero components to the each node. Okay. And basically, if it's between 0 to n, that is 2. Okay. And so if it is more than n plus 1, that should be 1. Okay. And if my rank equal 0, index 1 is equal to 1. Okay? And also, if my rank is equal to p dot, index n is equal to 1 for this one. Okay? And so we just accumulate this index value from 0 to np. Okay? So not 0 to n. And we just include all information, including the external node. So therefore, so NPLU, so total number of the zero components, is equal to index NP. Okay. Okay. So this is very important part. Okay. So any questions so far? Okay, so so here we need to specify the each items. Okay, so this part, so it's a little bit complicated. So I need to describe one by one. Okay, and yeah, we start with a very special case. Okay, so if my rank equals 0 and I equals 0, so this case. Okay, so we have only one non-zero octahedral component. Okay, so that is corresponding to I plus 1. Okay, and in other case, so my rank equal this one, and I is equal to n minus 1. So in that case, so neighbor is I minus 1. Okay. And otherwise, so it's a general case. So generally, it is equal to I minus 1 and I plus 1. Okay. But in the case of the, so I equals 0 here. Okay. So in that case, so this left-hand side is not I minus 1, it's n. Okay, so that's it, n. And if this is n minus 1, so this right-hand side is not n, so it's n plus 1, so you can see. So we have a, so n minus 1 and n plus 1 are the neighbors. Okay? And if my rank equals 0, and so I equals n minus 1. So in that case, neighbors of n minus 1 is equal to n. Okay, so it's a little bit different here and here. Okay. So this is how we do for the internal nodes. Okay, and in this case, we also need to define the non-zero octahedral components for the external point. Okay, so I will show you why we need this. Okay, so anyway, so we just define that. Okay, so I equal n, so this n is so external node. Okay, and if it's my rank is equal to 0, neighbor of this n is n minus 1. So otherwise, so they are all 0. Okay, like this way. And as for the plus 1, okay, and so if my rank is not equal 0, and my rank is not equal this one, so in that case, neighbors of n plus 1 is equal to n minus 1, because this is the only case. Okay? So that we can define the neighboring nodes, so items, okay, for all internal and external nodes. Okay. Okay, so please make sure. So there are no exceptions. Okay. Okay. So any questions so far? Okay, so next part is about the communication table. Okay. So we are constructing the information about the number of neighbors, naive dot, and the list of the neighbors, and also the import index and item, and export index and items. And finally, so we just construct the status and request for sending and receiving. Excuse me. Okay, so generally we have two neighbors. So in this case, okay. But if my rank equals 0 or p dot minus 1, we have only one neighbors. And if the total number of processes is equal to 1, so we have no neighbors. Okay, so we have some 3 exceptions here. And the idea of neighbor, first neighbor is my rank minus 1, and the second neighbor is my rank plus 1. But you can see, so in this case, we have only one neighbor, and that is my rank plus 1. Okay, and this one is not an exception, but so we just specify twice. So my rank minus 1 is only neighbors. Okay, and so next is so about import and export index and item. Okay, actually, so you can see in the case of the 1D, we have only one node to exchange with the neighbors. Okay, for example, so this one is a boundary node, and this is an external node, and we just send the information of the internal nodes, so boundary nodes to the neighbors this side, and this one to this side. And we just so receive the information of the external node from the neighbors, so just this one and this one. So therefore, import index 1 is equal to 1, and the import index 2 is equal to 2. Because so with the second neighbor, we have only one so information. And the import item is n and n plus 1. So they are the ID of the external nodes. Okay. And as for the export one, also we have a export index 1 is equal to 1, and export index 2 is equal to 2. And we are sending 0. Hello? Okay. And so we are sending the n minus 1 to the second neighbor. And we also have some exceptions, because in the case of the my rank is equal to 0, and so first external point is equal to n, and the first boundary node is equal to n minus 1. Okay, so that's it. So in the 1D case, so the size of the buffer, the sending buffer and the receiving buffer is equal to 1. It's very small data. Okay. So this is I just so shows so interface of the MPI I send and I receive and wait all. So I can skip the details here. Okay, so again, I'd like to show the generalized communication table. So this is a sending part. Okay, so the naive P dot is a number of neighbors. Naive P is a list of the neighbors. Okay, and the export index is a message size for each neighbor, and the ID of the boundary points are export index. Okay, and the message size to each neighbor is stored in send buffer. Okay, and this is how we use this. Okay, and so I have already shown this slide several times, and we just copy the value at the boundary point to the sending buffer, and so we are just visiting each neighbors, and the corresponding part of the sending buffer is sent to each neighbor. Okay, so this shows 1D case, general case. Okay. So you can see, so we have a 0 to n minus 1 for the internal nodes, and the n and n plus 1 are external nodes. And in this case, naive p top is equal to 2, and the first neighbor is my rank minus 1, and the second neighbor is my rank plus 1. Okay. And because we have only one message to each neighbor, export index 0 is equal to 0, and the export index 1 is equal to 1, and the export index 2 is equal to 2. Okay. And the ID of the boundary point is the first, so boundary point is 0, and the second one is n minus 1. Okay. So the send buffer values at 0 is copied to the first component, and the value at n minus 1 is copied to the send buffer, the second component. Okay, so this is a very simple case for the 1D case. So next one is the receiving. Okay, it's also the same. Okay, so in this case, we have external points n and n plus 1. And so this is a neighbor list, it's same. And also the import index 0 is equal to 0, import index 1 is equal to 1, and the import index 2 is equal to 2, because we are just importing a single node from each neighbor, like this way. Okay? So first component of the external node is n, and the second one is n plus 1. And the values at, so this n is equals the first component of the receiving buffer. And the second component is going to the value at this n plus 1. Okay. So this is a general case, but of course we can read some exceptions. Generally, we can do this way. And the next page summarizes generalized communication table. So this one was a Fortran. Okay, so because in the case of the Fortran, it's starting from 1 n. Therefore, the external points are n plus 1 and n plus 2. Okay, so you can see now p top is 2. And so neighbors are my rank plus minus 1. Okay. And the import index is 1 and 2, and the items are n plus 1, n plus 2. So export items are 1 and n. Okay. So if my rank is equal to 0, so we have some exceptions. And the import item is n plus 1, and the export item is equal to n. And the neighbor, first neighbor is my rank plus 1, okay, not minus 1. So this is a C case. Okay, so in the case of a C, generally, so this index and node ID are just a minus 1. Okay, so basically they are all same. Okay. Okay, so this is the end of the preparing the data. So we specify the number of nodes and element connectivity, and also matrix connectivity. So both for the index and items and the communication table. So including list of the neighbors. After that, so we can do the computations as we did before. Okay, so any questions so far? Okay. Okay, so next part is matrix assembly. So you may remember the matrix assembly part in the single CPU case on the PC, and it's almost same, and just a single page. And you can see, so there are no NP function here. Yeah, because we have a local data, so including this so overlapped elements. So therefore, so all the element computation can be done in local way. So therefore, we don't need any communications. Okay. Okay, so we are visiting all element and so picking up the IN1 and IN2 for the each element. So you can see, so we have no difference between the external node and internal node here. Okay, so we just try to compute for the both of the internal nodes and external nodes. And you can see, so this is the IN1 and IN2. So this is a length of the mesh. And this is parameters, and we can easily calculate the element matrix here. So in the case of the diagonal component, we just add the diagonal component of the element matrix to IN1 and IN2. Okay. And so another part is a non-zero of diagonal component. Okay. So actually, so this part is almost same as before. Okay. And so only exception is so this one. Okay. If the my rank is equal to 0 and I cell equals 0, so that means the real leftmost node, so leftmost element. In that case, K1 is equal to index IN1, and otherwise, K1 is equal to index IN1 plus 1. Okay. And K2 is index IN2, and we just add the non-zero components of the K1 and K2 to the off-diagonal component of the element matrix. And the right-hand side is just calculated by the this Qn value. Okay, so you can see it's almost same. So except this, we have additional condition here, my rank equals 0. So other part is just same. Okay, so this is a structure of the local matrix. Okay, and N is a number of internal nodes, and NP is the number of the all nodes, including external nodes. So actually, so you can see NP minus N is equal to the external node. And this is a matrix, and this is a vector. And this is just a N by N just for internal nodes. Okay, like this way. And if you want to compute the oops. Okay. Actually, so as you remember, if you want to calculate the matrix vector multiply locally, we need this rectangular part. Okay, so if you have this part, we can do the matrix vector multiply where this vector. So because this part has a length of the NP, and we can multiply these NP components, and we just do the N computation here, so it's okay. And so you can see, so this is a 3D case for the matrix vector matrix computations. And basically, so we are visiting all elements and calculating the matrix components. Okay. So basically, so we have this type of the local data set, and we are calculating the matrix components even for these external nodes. Okay. Therefore, we have this matrix now. So we have now the NP by NP square matrix. Okay. Of course, this black part. So this part where the external nodes are not complete. Because in order to have a complete matrix for this part, we need further external nodes. But actually, we just use the part, and we don't need this part. So therefore, we don't use this part. So therefore, it's okay. Okay. Yeah, that's why we don't have any communications, and also we don't have any else clause inside the computation of the matrix assembly. So if you go back to the this one, okay? So you can just keep the same way we did in the single CPU program, which we learned in the first day, okay? So this is because we designed a very sophisticated data structures, so with some overlap elements. Okay, so any questions so far? Okay, so next part is the boundary conditions. And so in this case, so boundary condition is just apply this part. Okay, so therefore, my rank equals 0 and I equals 0. So this boundary condition is applied. Okay, so therefore we skip the details. And this case is so almost no changes compared to the one CPU case. Okay, so we selected the matrix and also we finished the boundary conditions. And the last part is solving the linear equations, okay, by conjugate gradient method. Okay, first of all, so we allocate that these, so yeah, in this case, RZ, PQ, PB vectors are separately allocated. And the DD is equal to 1 divided by so diagonal component. And we are doing the, so this part is initial residual here, okay? So in order to do this initial residual, we start to copy the so boundary values of the X. So in this case, it's V, is copied to the send buffer. Okay, so you can see you are visiting the neighbors, and from export index to export next export index. And the export item K is equal to KK, and KK is ID of the boundary node. And the KK is not necessarily continuous, and this K is continuous. Okay. Okay, so we have several procedures: matrix vector multiply, product, conditioning, and DAXP. So actually, conditioning and DAXP are same as before, and like this way. So we don't need any changes. And you can see there are no MPI functions. Okay, so this is a matrix vector multiply. And so this is for the P equal Q. Okay. So first, we are doing the copy the value of P at the boundary node send buffer. Okay. And after that, so we are visiting all the neighbors and doing the MPI I send. And so initiate the sending part. And after that, so we are visiting also the neighbors, and we so initiate the I receive part. Okay. And after that, so we call MPI wait all which is corresponding to this receiving part. And finally, so we copy the value of the receiving buffer into the external point. So this is how we do the information exchanges at the process to process boundary. Okay, then we can get the most updated result for the external nodes. And after that, so we call the MPI wait all for the sending. So of course you can do that after this. Okay, and so we just do the matrix vector multiply. So you can see, so this loop is from 0 to n, and it's same as the serial code, non-parallel code. Okay, so you can see, so we are doing the copying the sending buffer and sending and receiving and wait all and copying to the external nodes. Okay, so this is a dot product. So it's RZ equal rho. And you can see we just calculate the local sum and we get the global sum. And we use the MPI all this. So this global sum is shared by all processes. Okay, I just show the MPI reduce and so yeah, I can skip this part. And we are applying corresponding this part. This is a Fortran case. Okay. And we use the MPI all reduce. Okay. Okay, so I just go through the convenient gradient method according to this one. Okay, so any questions so far? Okay. Okay, so first part is initial register, which I just show you. So copying the sending buffer and I send and I receive and wait all and copying to the external nodes and another wait all while sending. And we calculate the initial register here. And the binom 2 is calculated by this MPI all reduce based on the binom 2 0, where binom 2 0 is a local sum. And you can see, so this functioning part is same as before. We have no parallel statement. And this part is calculating row, and it's we are using MPI all reduce. And the next part is updating P, and you can see, so this part, there are no parallel functions. And this part is Q equal AP. So I have already explained this, and copying the P to the sending buffer, and calling MPI I send, and also calling MPI I receive, and calling MPI wait for receiving, and copy the receiving buffer contents to the external node, and call wait all for the sending part. Then we do the matrix vector multiply. So using CRS format. Okay. And alpha is equal to rho by PQ. And rho is shared by all the process. And we need to calculate the PQ. Okay. And this is so again we need a MPI all reduce. And we calculate the local value C10 and sum of these to C1. Okay. And this is MPI all reduce, and this C1 is shared by all processes. So alpha is equal to rho by C1. Okay. And the next part is updating X and R, and this is also, there are no parallel computations. And the next one is a binorm 2. And so binorm 2, 0 is so local value. And so MPI overviews, we get the denorm 2. And so legit, so checking the convergence is done by this value. So as we did in the single CPU case. Because both of the binorm 2 and the binorm 2 are calculated by MPI overreduce. That means the processes are sharing the same value of binorm 2 and binorm 2. So therefore, so value of logit is the same for all the processes. So that's why so we can do this type of the so if then else clause, and if this logit is smaller than so criteria, we can go out. So otherwise, we repeat the process. Yeah, in this case, we are sure that all the values are same for the all processes, but you need to confirm that. Especially if you include this type of the branch. Okay, and then this part is a output part. Okay, so we write the residual, and we also so provide the time whether my rank is equal to 0. So we apply S1 time and E1 time before and after matrix assembling. And also we put the E2 time after linear solvers. So therefore, so if you the E1 time by minus S1 time shows the time for the matrix assembling. And the E2 time minus E1 time shows the time for the linear solvers. So you can evaluate the parallel performance by this way. And finally, so we are writing the result at this point. Okay? So at this point is corresponding to the my rank is equal to P dot minus 1. And so this is a number n node on this process. So therefore, pi minus 1 should be so printed here. So that you can so compare the result at this point. So even if you apply the parallel computing. Okay? So this is a very brief overview of the parallel version of the 1D code. So you can see mostly we spend time for the clearing the data. Okay? So as I mentioned, data structure is very important for the parallel finite element. And you can see, so main part is not so different from the original code on the single CPU. Of course, in the case of the conjugate variant method, we have several additional terms. So because of the parallel computing using MPI. But it's very limited just for the dot product and the matrix vector multiply. And so matrix assembly part is so kept same as before. And yeah, because so we have reasons. So one is so finite element method is a very local method and element by element. So that's why we can, so the parallelization is very, very easy, and there are no large amount of the additional functions for the parallel computing. So another reason is that we designed a very sophisticated data structures, so we don't need to consider the parallel computing. Okay. Okay, so let's see the final part of this sections, and I show you the some results Okay. So what is validation? Okay. So validation is very important. And so even if you have a good parallel scalability, if the results are not correct, so yeah, it's nothing. Okay. So you need to evaluate that you are you get the answer. Okay, so this is a case for the 1,000 elements, and so up to 1 to 48 processes. Okay, excuse me. And you can see, so this is analytical solutions, and so 500,000. Okay, at this point, and you can see for the so all cases, so we have the same number of iterations until convergence. And so proper answer, okay? And so it's validated. So if you want to validate your code, so you should do like this way. So you just compare with the result with a single CPU program with a small cases. Okay. Of course, if the original code is wrong, so you cannot get the proper answer. But so if it's correct in the single CPU case, you can validate like this way. And you can see the number of iterations don't change. Okay, so even if you apply the parallel cases, okay, because outside the reason. So the reason is so it's very difficult to say that so they are doing the same computations except communication. Okay, so therefore, yeah, if you are doing that communications, so you can get the same answer with the same number of iterations. And this is a parallel performance. Where so this one is actually the not element number. Okay, so 1 million and 10 millions. Okay, and you can see, so if you compare the speed up, you can see the performance of the 1 million case is a little bit saturated if you apply the large number of cores. And this is a parallel performance which I mentioned yesterday. And so actually up to 12 cores. Okay, so it's perfectly scaled, but it's getting a little bit slower if you increase the number of the cores. Okay, but so you can see the decreasing of the parallel performance for the smaller case is significant, and so up to the so in this case we have many nodes. Okay. So in this case, you can see, so only 80%. Okay, so it's not so bad. Okay. So therefore, so you can do this type of the evaluation of the parallel performance. Okay, so I talked about this performance decreasing. So one reason is the time for MPI communications, and another one is the time for starting MPI, so-called latency. And another reason is the synchronization of the MPI. So in our case, so again, the message size is very small. So we are exchanging only one data, okay? So that means the 8 byte with the neighbors. So most of the overhead is by this time for starting MPI and synchronization. Okay. Okay. So this is a summary of this part, and I hope you understand that the proper design of data structure of distributed local meshes is very important. And we still have open technical issues. The parallel mesh generation, parallel visualization, parallel conditioner, preconditioners for ill-conditioned problems, and large-scale I/O. And so next, I'll talk about a 3D parallel case, and I'll show you some of the answers for this part. But so we still have big problems. Okay, so I'd like to show this slide again. So yeah, distributed local data structure for parallel computations. So I hope you understand how important to design this kind of the sophisticated data structures. And everything is easy if the proper data structure is defined, and the values at boundary points are copied into the sending buffers and send and receive, and also wait all. And values at external points are updated to receiving buffers. Okay, so I just show you some examples. If the numbering of the external node is continuous in each neighboring process. Currently, so we assumed the numbering in each neighbors are not necessarily continuous. But generally speaking, it's much more efficient if the numbering for each neighbor is continuous, like this way. We have 64 internal meshes, and we have this kind of the halo or sleeve area. Okay? We have 8 external points with each neighbor. And if you see the numbering here, so it's 65 to 72. And this one is a 73, 74, 75. So you can see it's continuous up to 80. And this one is also numbering itself is continuous up to 88. And this one is also continuous. So in this case, we can utilize these features and for more efficient communication. And actually, so it's very easy configure this type of continuous numbering. Okay. Okay, so this is a original part for the AP call queue. So in this case, we are copying the sending buffer and send and receive and wait all, and then copy the value of the receiving buffer to the external node. Then we call wait all again. So if you see the 1D.c, which is in the same directory, yeah, we can do a little bit faster. And in this case, we utilize the features where the numbering are continuous in each neighbor. Actually, so in the 1D case, we have only one external node for each neighbor. So in that case, every time numbering is continuous. Okay, so in this case, we can avoid the copy for the external node. Okay. So this is what we are doing now. So in this case, and also we can keep the MPI wait for just once. In this case, we need to combine the sending part and reading part, sending part and receiving part. So therefore, the total number of neighboring process is doubled like this. Okay, and so you need to allocate the larger static state and the request sending. Okay, and the sending part is same, and the receiving copying part is same for the sending, and MPI send. And instead of using the receiving buffer, so we can directly receive the value, but external point like this way. Okay. So therefore, we don't need the copy here. Okay. That means we don't need to commit over here. Okay. So therefore, we just call wait for just once. So after this, so receiving. Okay. So you can see the code is much simpler and also it's efficient. So in the case of the 1D, the effect is not so significant, but so you can compare the performance between 1D.C and 1D.C. Okay. So this is the end of the 1D parallel case. And so any questions or comments? Okay. Okay, so now time is 7 minutes past or 8 minutes past the clock. And so next set until 3 o'clock will be the exercise because probably you didn't develop your own 1D code, and I'd like you to run this 1D code and so understand what is happening. And I would like you to starting with the validation and also make some plays different number of processes and compare the performance. Okay. And so we start the lecture at 3. Okay. Okay, so you can take a break, and so after that you can go back and do exercise. Okay, thank you. Okay, so let's start 3D part. Okay, so any questions so far about 1D parallel part? Okay, so let's move on to the 3D part. So first, we try to parallelize the 3D code using MPI. And we extend this to the hybrid with combined with OpenMP. Okay, so this is the procedures. And the first, please copy the file to your directory. So it's a Fortran and C, and name is the fm3d.tar. Okay, and please don't forget this blank dot. Okay, so this is the Fortran case, and this is the C case. And if you so open the archive, so you can get so 3 directories here. So MPI is already created, and you can see FEM3D and PFEM3D. And we are mainly working on this PFEM3D because FEM3D is the same program which we had on the PC. Okay, so we need this program to compare with so parallel version. Okay, so please copy the files, and please let me know if you have any problems. I believe we have no problems for the permission. Okay. So if you have copied the files, please compile the mesh generator, domain partitioner, and the parallel finite element code. So first, please go to this PFM3D mesh directory, and so please type module load fj, and so compile the mesh generator. So this is a Fortran code. Okay, so even if you are a C user, please so install the Fortran version. Okay, and the next one is the domain partitioner, and please go to this part directory and type module blank load blank metis slash 4.0.3 and make. And so make sure this mesh part is so created. Okay. And finally, please go to the this src directory and type make. Then you can get source file in this run directory. Okay, so after copying the file, so please install these three functions. Okay, so mesh generator, partitioner, and finite element solver. So last one is a parallel finite element applications using MPI. And please raise your hand if you have any problems or questions. I think. Okay. Any questions or problems? Is it okay? Okay. So let's go to the next part. Okay. So I just show you the how to run the code. In the case of the parallel finite element, so we have a little bit complicated procedures. So first, you need to generate the initial global mesh. Okay. And so next one is so distributed local mesh files using partitioner. Then finally, so you can do the parallel computations. Okay. And so mesh generation is done by this mesh directory, and partitioning is also doing this mesh directory. And so running the code is so on the run directory. Okay, so this is the procedure. So this part shows so program, something like a button, and this drum type object is a mesh. So this one is a initial mesh file. It's a single file, and you can see. So this is a distributed file. Okay, and so we have some control file here, and we have some so this INP, so paraview file, okay, like this way. And you generate the mesh file by mesh generator, and doing partitioning, and you have so some distributed mesh file. And with this distributed mesh files and control data, you can solve the problem. Okay. Okay, so yeah, before going to real computations, I will talk about the domain decomposition and domain partitioning. So partitioner so creates the distributed local mesh files from initial global mesh automatically. Okay. So in the case of the 1D case, so actually, so you generated the distributed mesh file so in the program, but you need to consider the various kinds of the exceptions. And basically, it's by program, but mostly it's by hand. But in the case of the 2D or 3D, it's impossible. Okay, so therefore, we need some automatic tool. So partitioner is doing such kind of works. Okay. And the partitioner creates internal and external points and distributed local mesh files. And so numbering is so this way. And the communication table is also so created automatically. So communication tables includes information about the neighbors, number, and list. And the external points and the boundary points information, such as import index and import item, or export index and export items. Okay, so what is partitioning? So partitioning is so basically graph partitioning or graphic partitioning. So this is a more general name. Okay, it's a procedures and operations of domain decomposition and domain partitioning or parallel computing. And partitioning means creating distributed local mesh from huge local global mesh, which cannot be handled by a single process. Okay. Graph partitioning or graphic partitioning is so applying the graph theory for graphs to the domain partitioning in parallel computing. So actually, so definition of a graph is a set of vertices and edges like this way. Okay? And so I believe some of you are from a mathematics department or computer science department, and some of you some classes named the graph theory. Okay, and so yeah, typical topics in the graph theory is a one-stroke sketch or a four-color problem. So it's a very fundamental issue, and so graph theory is very convenient for this kind of the partitioning method. Okay, yeah, like this partitioning. So in this case, the graph is very small, but so this is so one example. Good partitioning is so good load balancing, okay, and small communications, and sometimes convergence of the preconditioned iterative solvers is affected by this amount of the communications, okay, and also minimum number of neighbors. So we have several kinds of the restrictions for good partitioning. So edge cut, yeah, I think, yeah, for example, this kind of the so domain boundary is called edge cut. Okay. So this is a oops, sorry. So this is a no edge cut case, and the edge cut case we have a different colors or different partitions. So generally speaking, so smaller number of edge cuts provides a smaller communications. And so this is a better partitioning. Okay, so let's think about the two types of the domain partitioning for the 2D geometry. So this is a 15 by 15 squares, and that is divided into 16 processes. Okay, so you can see 16 small domains, subdomains in each square, and basically load is balanced. Okay, and so the difference of the number of meshes in each partition is the difference is 1 or 2. So very well balanced. RGB and RSB are some name of the method for this kind of partitioning. So actually, these methods are not really used in recent days. Okay, and so RGB stands for the recursive graph bisection, and RSB stands for the recursive spectral bisection. So I don't get into the detail of the algorithm itself, but so if you compare these two partitioning, so which one do you like? Okay, or which is more beautiful, or which is more seems more efficient. Probably this one. Okay. So why this one seems better? Because 16 means 4 by 4. And so you can see, so 15 is not divisible by 16 or 4. So that's why. So it's a little bit complicated. But so this one is similar to 4 by 4. But on the contrast, so this one is a very irregular. So you can see, so these red guys are so very thin and are not so beautiful. Okay. But actually, so quality of the partitioning is better for this one, especially from the viewpoint of the edge cut. Okay, so this one has many edge cuts, and this one has a pure edge cut. Okay, so this is actually I solved the problem of the Poisson's equations on this geometry. Okay, so this result is actually many years ago. So almost 30 years ago when I started this kind of work. Okay, and so we are solving the Poisson equations on the two geometry. So you can see we have a different convergence history. So in this case, we apply the localized ILU type conditioning method. So it's more sophisticated than point Jacobi. And in this case, so we have a different number of iterations according to the different partitioning. Okay, and you can see, so we have this one. So red one provides a much better convergence compared to this one. And this result is done by the fewer edge cuts in the RSB. So that's this right-hand side. And the larger one is coming from this more edge cut for the RGB. So these are comparing some statistics, and you can see boundary edges means edge cut. So average number for each partitioning, average number of the edge cuts for each partitioning is so more than 15 for this RGB. But in this case, it's 12.5. Okay. So roughly, so not 20%, but 15%. So it's better. Okay. And this so provides a very different convergence rate. Okay. And this is so one of the examples, but generally speaking, so if you have a partitioning with fewer edge cuts, so that provides so fewer communications, that means so better convergence for this type of the preconditioning method. So there are several methods for partitioning, and many research groups in late 1990s. So it's more than 20 years from 20 years ago from now, and Metis and Scotch or PT Scotch are the two major tools. Okay, Metis was developed in the University of Minnesota, and the Scotch or PT Scotch was developed a little bit recently. So it's a French tools, not a Scotland. Okay, and Johnson was another very famous tool in early this century. It was developed in the University of Greenwich, so in UK, but now it's not so. The group is active. So in this class, we are using this Metis. Okay, so if you go to the PFM 3D mesh part, so you just compiled, and the code itself is a Fortran, written in Fortran, But today, I don't get into the detail of the partitioning itself. But so if you want to be familiar with the partition itself, so you can just read the code. And if you have any questions, please ask me. Yeah, actually, so I developed that partitioner so many years ago, and I don't remember the detail. But and also that is not so efficient code, and there are some rooms for develop improvement. But so if you are interested in and have any questions, please ask me. Okay, so this partitioner so partitions initial global mesh file into small subdomains. So it's a serial operation. It's not parallelized. And it also creates distributed local mesh files with communication tables. Okay. And we support several methods for partitioning. So RCB is a recursive coordinate bisection. It's a very simple method for dividing according to the axis. Okay. And we also support METIS. Okay. And there are several methods in METIS. And we are supporting both of the K-METIS and the P-METIS. And the K-METIS so minimizes edge cuts, and the P-METIS optimize so load balancing. So it's so yeah, we can use both of these. Okay, so actual large-scale computations. So as I mentioned yesterday, large-scale mesh generation is still a big technical issue. Okay? So one of the direction of the large-scale mesh generation is like this way. Okay? So we start from the rather coarse mesh, and we divide into the parallel part. And we apply the local mesh refinement. Okay, yeah, it's usually used as a adaptive mesh refinement. So we apply the finer mesh, and we adjust the boundary, okay, to get the consistency. Then so we can get that very fine distributed meshes. So this is one of the direction, okay? But anyway, so we start for the some mesh and the partition into the small ones. Okay, so next slide describes a very brief overview of the RCB, which is supported in our tool, so recursive coordinate bisections. So details are written in this paper, Partitioning of Unstructured Problems for Parallel Processing. It's a very old paper, more than 30 years ago. And in the previous slide, I showed you the two pictures of RSB and RGB. So the details of the algorithms are also described in this paper. And if you are interested in that algorithm, please read this paper. So basically, recursive coordinate bisections algorithm is very simple, and comparing XYZ components, and the reference axis can be selected according to the geometry. And the continuous partitioning along x-axis for a cylinder object is possible. So basically, so it's only 2 power of n processes, but you can easily, you can easily modify the method in a more flexible way. And this is very fast, and so yeah, especially for the very simple geometry. This is the idea. So you have a target object, and you apply the reference axis. So in this case, it's a x-axis. Okay, so we have a balanced partitioning like this way. And the next one is 1, right? And so totally you have a balanced, well-balanced partitioning. Yeah, just continue this way. Okay. So METIS is based on the multi-level graph theory. And so it's very complicated. And if you are interested in, so you can refer the reference. Okay. So this is a multi-level partitioning algorithms. And so you start from the graph. And this small picture shows that they are merging the some graphs into the small ones. And so apply the partitioning as a very close graph. And so we are going back to the fine graph, and so do some optimization to minimize the edge cut. So this is a very brief overview of the METIS. So it's very fast, and it's very robust. Yeah, stable and fast, and also it's free. And we have two versions. One is the standalone, and another one is the library versions. So in this class, we are using the library versions. And the various procedures. So I have already mentioned about the K-METIS and the P-METIS. And also they have a parallel version. Okay, it's a distributed parallel version, and it's very convenient. And I believe they also have a multi-threaded version recently, but I have never used that. But so it's a variety of methods. And so this can be utilized for various types of applications related to graph, and such as ordering or data mining, etc. So METIS was developed by Professor Karipis. He's a professor at the University of Minnesota. He's originally from India. So at one meeting, so almost 2 years ago, so we are in the same session, and he presented at the parallel contact search for crash problems, so car crash. So yeah, that's the application with the METIS. Okay. And so such kind of applications are also feasible. Okay, so I'll show you some examples of the partitioning. Okay, so this is a very simple cube, which we are now doing in our class. Okay, so in this case, we have 4,096 nodes, and this one is so division by K-METIS into 8 processes. And this one is a RCB. So this red so that shows a so-called overlap element. Okay. So if it's straight, so we have a smaller number of edge cuts, and if it's thin, it's better. Okay. So you can see in the case of the K-METIS, so in some reason, so they have this type of the so kinked ones. So therefore, we have a more edge cuts compared to this one. But this is the only case where the RCB is better than K-METIS. So if you apply more complicated geometry or more real-world geometry, so generally METIS is much better. Okay, so for example, this one. So you can see the edge cut number is doubled. And this one is a very complicated one. So we have a cylinder, and we have some so discs here, and you can see we have a small hole here. So it's for the mesh. It's a mesh for some heat exchangers. Okay, so in that case, the edge cut number is 3 times. Okay, so this one is a dinosaur. So Triceratops. So this one is a K-METIS, and this one is a RCB in 8 part. So you can see, so in the case of the K-metis, they try to divide into the, so this foot part, head, and the body, and so fore, back, legs, and the tail. But in the case of the RCB, they just try to divide the mesh into the X and Y and Z direction. And this is not so practical. Okay, so if you see from behind, yeah, this one is very nice. So the tail is a one version. But you can see in the tail part, we have a very so complicated domain boundaries. So this one is a gate. Actually, so this is a red lacquered gate in University of Tokyo. Okay, so actually, so it's very simplified. And this one is a K-metis, and this one is a so recursive coordinate bisections. Yeah, so it's a very different number of edge cards. I think I have movie here. Yeah, this is starting from the so RCB. Okay, and you can see it will be changed to metis. Okay, so that's much better. Okay. So this is a so comparison between K-metis and P-metis. Okay, and you can see so K-metis is better for the edge cut, but not optimum for load balance. Okay, and this one is better. Okay, so if you compare the edge cut, this one is better. Actually, so choice of the K-metis or P-metis is so up to the applications. Okay, and also the situations. Yes. So anyway, so if you are trying to use this type of the partitioner, yeah, you should so evaluate using the simple problems, which is better for your application. So anyway, so there are several approaches. And this one is so Southwest Japan. It's a mesh for the earthquake generation cycle at this subductive zones. So we have a very complicated plate structure, so near Japan, and also I think that Taiwan is also included in this area. But in this mesh, so it's just around the Japan island. So this one is RCB, and this one is METIS. And you can see, so this subductive zone is so clearly modeled and separated in the case of the METIS. But again, it's also included here. I think I have some movie. Yeah, I start from the RCB, and you can see we have some mesh lines here. Okay, so you can see in the case of the so this METIS, so this partitioning is along the mesh lines. So generally speaking, so METIS provides a more flexible this kind of partitioning. Okay. Any questions so far? Okay, so let's go to the real executions. Okay. So this is a procedure for the parallel finite element method. And so first, let's create the global mesh. Okay. So in the case of the PC case, so if you type ./mgcube, so you are asked to enter the mesh number in each direction, and you just enter the number. But in this case, so on the supercomputer, basically it's not allowed. So therefore, please use batch job. Okay. And then we have a mg.sh. So mg.sh is a shell script in your mesh directory. And this is using one node and a single core. And so dot slash mg cube, and so int mg is so input. And this 2020 is so input by mg. And yeah, you can do this on batch manner. Okay. And the domain decompositions and partitioning. So file name of the initial global mesh is fixed. It's a cube.0. And RCB and METIS are supported. And the header of distributed local mesh files are specified. And work is not allowed as a header name because work is used as a work file inside the program. So in the case of the RCB, so you need to specify the number of processes and the reference axis. In the case of the METIS, you just specify the number of processes, number of the partitions. Okay, so this is a make file for the partitioning. Okay, so you can see, so you are using this METIS library here. Okay, so in order to use this library, so you need to load the module for the METIS 4.0.3 as you did. Okay, so this is just, and actually, so the original program, so it's interactive. Okay, so type./path, and you are asked to input the original so grid file. So it's a cube.0. And they provide some information, total mesh number, total element number, or some group number and edge number. Okay. And you are asked to enter the method RCB, KMetis, and PMetis. And if you select one, so it's RCB. And you are asked, so how many actions you are made. So it's a 2 power of n. Okay, so if you put 3, that means so we have 8 regions. And the next, we are asked to input the header of the distributed file. So just put AAA here. Okay. And the next, so you are asked to enter the reference direction. Okay, because we are applying 3, so you are asked 3 times. First one is X. So if you X 1, that means X direction. And the 2 and 3 means Y and Z. Okay. Then, so they are starting the partitioning. Yeah, total number of edges, total edge cut. Okay, so I think it's after the partitioning. And so it's a number of nodes in each process. So you can see it's almost balanced. Okay. And this is a number of the overlapped elements. And this is a list of the neighbor partitioning. Okay. And finally, they are writing the information like this. And the first one is a number of nodes, internal plus external. So this one is internal nodes. And this is a number of external nodes and the boundary nodes. Then it's terminated. And you can see we have AAA.0 to 7. So we have 8 distributed mesh files. So it's created. So distributed local mesh files is a header dot ID of rank ID of processes. And so rank number starting 0. So again, so this interactive information is not allowed, and please submit the batch jobs. Okay. So we prepared some so sample shell script. Okay, part rcb.sh. So this is for the recursive coordinate bisections. And basically, so we have one process and one node, and the dot slash part, and we are reading imp RCB. Okay, so this is the content of the imp RCB. So actually, so all the information which we entered in the previous page by these red letters are included in this imp RCB. Cube.0, so method for the partitioning, so number of axes, and the name of the header, and the reference axis. So in this case, so we have three partitioning, so we have three numbers here. And if you want to create a single CPU model, you just apply this imp RCB this way. Okay, RCB, and so number of partition is, if it's so 0, that means that we have only one partition. Okay, then you can get the single CPU model. So this is another case. So part kmetis.sh, and so you can see, so this imp kmetis means so name of the initial file is fixed, and kmetis for 2, and the number of processes. So if it's 8, it's okay. And finally, you need to specify the header of the name. And this is for the images. Okay, so only difference for the images is so this second number is 3. So this number selects the images. And if you run the code, so you can get the partition.log. So this is some record for the partitioning operations. So basically, the information which displayed in this interactive part will be just printed. Okay. Okay. So after creating the distributed mesh files, so you can run the code. Okay. And this is the input that. So this is a fixed name. And so first of all, so you need to specify the name of the header, okay, of the distributed local files. And in this case, something in the mesh directory is specified. Second line is number of the iterations. And so third line is the conductivity, and so these are heat generation rate. And the last one is convergence criteria for the conjugate gradient method. So basically, it's the same as we did in the PC case, okay? But the first line is a little bit different. So this provides information about distributed local mesh files. Okay, so this A08SH is using the 8 nodes and so 384 partitions. And then we have several configurations. So yeah, you can do this. Okay. So let's try to do the mesh generation and partitioning and run the code. Okay. First, so you can run the program. Okay. And please go to the mesh and modify imp mg and mg.sh and imp kmetis. So basically, so imp mg is a 31 by 31 by 31. Okay, so please change to that. And the imp k-metis is a cube.0 and the 2 and 8 partitions. So name is AA. Then first you submit the mg.sh, and after that, so you submit the part k-metis.sh. So in this case, we have a 31 cube element, so that means 32 cube nodes, okay, totally. And this is a partitioning method. And you can find test.sh in the directory. So this is in the run directory, and this is the input data. Please modify input data. And also test.sh in this way. So please be careful about the lecture 7.0 and the GT17. Then you can run the code. And finally, so if you run the code, you get the result. It's a test.list. Okay, so it's written in here. And you can have the convergence, and also you can find this file, this information. Okay, and this information shows temperature at origin. Okay, so I think this 3 and 1 are the partition number and local node ID, and this value is very important to validate the solutions. Okay, so even if you have the different configuration of the parallel computing, so you get the same answer as long as you are using the same initial file. Okay. So actually, so you can validate this program. So go back to your PC code, and yeah, 31 element, and you can create. So you can get the same result. Okay. Okay, so I think you should do this. Yeah, please do these operations before going to the break. So now it's at 3:55, and please do these examples. And so take a break, and we start the last part at 4:10. Okay. Anyway, so I give some demo here. Okay. Okay, so FM. Yeah, you can do that by yourself, but I also show you how to run this. So please go to the PFM 3D, and so you have already go to the mesh, okay, and so mg.sh is here. That should be 17 and lecture 7.0. And you need to modify the in mg. Okay, so it's 31 by 31 by 31. So first, so you should submit this mg.sh. Okay. Then you can prepare the part kmetis.sh. Okay, so this one is also 17. And you can see, so you are loading the Metis library here. And you need to edit kmetis. And yeah, it's okay. Okay, so in this case, you are creating AAA dot something. Okay, and the mesh generation is already done. So let's submit this part kmetis.sh. Okay. Okay, it's finished. Then please go to the run directory and Emacs input that. So this is should be the mesh and AAA. Okay. And also you need to edit the test.sh. Test.sh is like this. So you should change this. So in this case, you are using one node and 8 processes, so 8 cores. Okay, so you can run the code by test.sh. I think it doesn't take a long time. Okay, it's finished. And you can take a look at the file. So yeah, it takes 95 iterations. And in some reasons, so okay, so actually this history is written from the process 0, but these results are written from the other process. So in this case, results provides earlier than the history of the convergence, but it's okay. And you can see, so this is a 1.262583 per 4, and I think it's a correct result. So actually, we can do this, validate this on the single CPU code. Actually, so I have a code on the okay. G Fortran mgq.f. And for example, if you run the 31 by 31 mesh generation here, and so yeah, you can see, so same number of iterations and the same result, okay? So by the single CPU code. Okay, so like this way, so you can validate your code and also explains the parallel computations, starting for the initial mesh generation, partitioning, and parallel computing. Yeah, by the way, I want to say that so if you go to this mesh directory, so you can get this distributed mesh files. Okay, so you can have 8 partitioned files, and in the next part, so I explain the details of each local data file. For example, this is inside of this mesh files, and you can see so bunch of the numbers. Okay. Okay. So I think it's a good time to take a break, and also you can run the code by yourself. Okay. And let's start the next session at 4:10, as I mentioned. Okay, so before going to into the detail of the data structure, actually, processes of the mesh generation and partitioning are not parallelized. So therefore, it is very expensive in the following cases. So for the very large scale meshes or more domains, okay? And parallel mesh generator is also available. And so generally, so this procedure is used in this class. But partitioning using metis is very flexible. So we can utilize both. And in the next part, I'll just so show you the overview of the parallel mesh generator. Okay, because in the case of the serial mesh generation and serial partitioning is very expensive. But if you apply this parallel mesh generations, so they do the mesh generation and partitioning in totally parallel manner. So it's very fast. Okay, so I think this number is wrong. So this should be 17. So it's your ID. Okay. So, oops. And please go to your directory, and you can find so pmesh directory here. And so I think you should. It's better to copy my file from here. I think just a moment. I should check. Work DT00 share. Yes, I think it's better to copy the file to here. Just a moment. Okay. And please compile by this way, and you can create this pmesh. And modify mg.sh and mesh.imp in this directory, and pjsub mg.sh. And let's consider the very simple case where we have 5 meshes and 24 so nodes. Okay, this type of the very small meshes. So this is examples for creating the 2 partitions. Okay, so we have basically 3 lines in the so this mesh.imp. So first line shows so 3 integers. So this means the number of nodes in each direction. So for the global mesh. So in this case, we have 6 in x direction, 2 in y direction, and 2 in z direction. So this means so 6 by 2 by 2, totally 24 meshes, grids are generated. Okay. The second line shows the number of divisions in each direction. In this case, 2 by 1 by 1. So this means so we have a 1 partition here in x direction. Okay? And each of the component of the first line must be divisible by each of the second line. Okay, so this is so essential. Okay. Actually, so this mesh data is not so flexible, so please keep this rule. And the last one is a header of the distributed local mesh file. Okay. And this is a mg.sh. And so actually, so if you multiply this, the second line, ndx, ndy, ndz, so this means the total number of the partitions. And in the case of the mesh generator, so this process number must be identical with so that number. So in this case, 2. Okay. So by this way, so you can do the totally parallel mesh generations. Okay. And please modify this so memg.sh in so lecture 7 and GT17. Okay, and the P mesh. Okay. Okay, so I think yeah, this is some so more feasible examples, and so actually, so you can compare the result with a previous case with the k-metis. Okay, so in this case, you are specifying the number of nodes, not the element. So in this case, so mesh.imp should be this way, 32 by 32 by 32. And so then you create a mesh with a 31 cube elements. And the 2 by 2 by 2 means 8 partitions. Okay? And the mg.sh must be like this way. So a single node and 8 processes. And so you can run the mg.sh. And after that, so please go back to the run directory. And if you change this first line, dot slash pmesh pcube, so you can run the code using this mesh files. And finally, so you can get the same result. Okay, so you can just make sure about that. Okay, so now I just show you some demo on the screen, and you can try that by yourself later or now. Okay. Okay, so please go to the pmesh, and so before that I should check the okay, so this one is okay. And work GT00. So this is my directory. And so pfim and C and pfim 3D and pmesh. Okay. Okay. So you should copy the so GT00 share pmesh pmesh.f. Okay. Oops. Okay, and pi port px minus k fast pmesh.f minus small o pmesh. Then you can create this oops. Okay, it's created. So you don't care about that. And this is a mesh.imp, and you can see 32 by 32 by 32 and 2 by 2 by 2. Okay. And so mg.sh, and so you can see, so this should be 8. Okay. And if you submit this mg.sh, oops, you have a wrong group number. So you are creating the disputed mesh files. Okay, so it's created on the P cube. Also, okay, so you can have 8 meshes. And please go to the run directory and so input that. So you should use a pmesh pcube, okay? And open the test.sh. And in this case, it's better to change the name of the output file, okay, to compare with the previous one. And pj sub test.sh, okay? Then you can run the code. Okay, it's finished. And you can compare the previous one and the current one. Okay, so previous one was done by K-Metis. And you can see probably the same number of iterations and the same so residual. So you can see the same convergence here. Okay. And also if you compare the result, so this one is this result, and I remember, so this one is at the top. Yeah, if you compare the result, so it's also same. And basically they are solving the same problem, but a different way. So different way means a different partitioning, okay? But so they are solving the same problem, okay? Okay, so let's go to the next part. Okay, so let's think about this geometry. Okay, we have so these are 6 by 2 by 2 by and 2 by 1 by 1. So very small mesh. And if you generate this type of mesh, so this is the initial global mesh. Okay, and you can see we have 24 nodes, and you can see we have 24 nodes. And you see, so first and 6 are in this way. So 7 to 12, 13th to 18th, and 19th to 24th. And you can see this coordinate, okay, like this way. And then next we have 5 elements, okay? And so this is 5. And also these are the element type. So we have 361 and 5 element. And the next 5 line shows the node ID for each element. The first column is so element ID. So next one is a material ID. And the next one is so each node. Yeah, for example, first node is 1 to 87, 13, 14, 20, 19. Okay, 1 to 87 and 13, 14, 20, 19. Okay, so next part is so node groups. Okay, we have 4 groups, and so basically X minimum has only 4 nodes, 1, 7, 13, 19. But other part has so 6 by 2, and you mean that 12 nodes, and 4 plus 16 is 12. 4 plus 12 is 16. 16 plus 12 is 28, and if you add 12, it's 14. No, 40, sorry. Okay, so I just skip the details, but you can see these so node groups. So what is happening? So if you apply the so parallel mesh generations. So actually, this parallel mesh generation is corresponding to the RCB in X direction. So we have 2 partitions here. So this is the p cube dot 0, and this is the p cube dot 1. Okay, and so they are all global numbers. Okay, and you can see, so this number 3 element is shared by each part. And you can see, so these blue parts are so external nodes for each partition. Okay, so we have information about the neighbors, nodes, and elements, and communication table for import and export, and node groups. Okay, so yeah, basically based on the method which I mentioned several times, and the internal nodes, connected elements, so overlapped elements, and external nodes. So this is a fundamental structure of the distributed local mesh. Okay, and this is a numbering rules, and this is a communication table. So this is examples of the boundary nodes, and this is so external nodes for so receiving. Okay, so this is each of the p cube dot 0 and p cube dot 1. Okay. Actually, so I just skipped the so large digits, so it's a small digit to keep the so big font. Okay, and this is the beginning part of the p cube dot 0 and p cube dot 1. So actually, so this is already by the local numbering. Okay, and each partition has a 12 internal nodes and 4 external nodes, like this way. And you start from the internal node, so that's why. So the external node has this 13 to 16. And I think the element number is still the global initial numbering. Okay. Okay, so this is the beginning part. And the first line shows the ID of each process. Okay, this is 0 and this is 1. And the second one is a number of neighbors. Okay, so in this case, we have only 2 parts. So the neighbor number is 1. And the next one is a list of the neighbors. But in this case, we have only 1 component. Okay, this is the first part. So in this program, so we adopted a very special method for numbering. So, okay. And basically, the local node ID starts from 1 in each process. And so, yeah, we can apply the same program. And so numbering is starting from internal to external points. And the special numbering is so this double numbering. Okay. So in this program, so node ID has 2 components. Okay. And the first one is a local node ID at its home process, where the node is an internal node. And the next one is a node ID of the home process. Okay, so the second ID means so ID of the process. Okay, so actually we just apply this data structure, but actually don't use that. But this data structure is very suitable for adaptive mesh refinement and dynamic load balancing, like so this way. So this kind of the so double numbering is a very flexible data structures, and if you want to develop this kind of code, it's very feasible. Okay. Okay, so I'll show you some details. And the next one is the number of the nodes. So 16 is the total number of nodes, and the 12 is the number of internal nodes. Okay, so both are same. So next, 16 lines shows the information of the node. Okay, and actually, so this circled number don't appear, okay, in the actual data, okay? But it's a continuous local node ID from 1 to 16. Okay? And you can see first 12 nodes are internal nodes and the other 4 nodes are external nodes. And you can see, so this is a local ID and this is a home ID. Okay? And you can see, so yeah, this number is corresponding to these circled numbers. And so these 12 nodes, internal nodes, number 1 to 12, and the home process ID is all 0. Okay? So this is also the case in this one. Okay? You can see it's a 1 to 12, and there, so local ID is 1 to 12, and the home PE ID is 1. Okay. So basically, so this home PE should be identical with this top one, okay, like this way. On the contrast, these 4 nodes, external nodes, so from the different part, okay? And the number 13 to 16 for the local ID is actually, so I think we have another, yeah, this one, okay? So these 13 to 16 is originally these nodes 1, 4, 7, 10 in this partition. So here we are just showing that, okay? And these 13 to 16 is really the number 1 partition, and so ID is local ID is 1, 7, 10, okay? 1 is 13 here, and 4 is 14 here, and 7 and 15 here, and 10 is 16 here. Okay? Does it make sense? Okay, so same sort of thing happens for this part. Okay? So you can see 13 to 16 is actually 3, 6, 9, 12, where this process is 0. And you can see, so these are local ID here, and home P is so described here. But actually, so in the real program, okay, we just use so this continuous number. So we don't use these double numbering. But I just let you know this kind of the data structure is sometimes very flexible for the very distributed applications. Okay? So generally, so in the case of the finite element, so mesh is fixed. Of course, sometimes it's adaptive meshes, but basically they don't move. But if you are so adopting some applications using some particles, okay, so they move very dynamically. So in that case, so this kind of data structure so helps so efficient parallel computing or reconfigure the situations of the partitioning. Okay. So anyway, so this is one of the method, and but we don't use this. Okay, only local IDs are used in the program. Next part is the element. So we also define the home process of the element. Okay. It's defined by the home of the 8 nodes. Okay? And if all of the 8 nodes are internal points, home of the element is that of 8 nodes. Okay? For example, so this one and this one and this one and this one are all internal nodes. So in that case, so these 2 are belonging to process 0, and these 2 are belonging to process 1. And we have a problem for these wrapped elements. Basically, they are same. Okay? If external nodes are included, the smallest number of ID of home of the node is selected. And in this case, home P's of elements in overlapped regions are all 0. So in this case, you can see, so this element has a, so only, so 0 or 1. So in this case, 0 is the home of this element. And you can see, so in the first line, we have a two information for the element number. So first one is a number of all elements, 3, okay? And the next one is a number of the local elements, okay? So in this case, we have only two local elements here. And so these 3 are local elements for this case. So next number shows the type of the element. So in this case, all 361. So the number is corresponding to the all elements. So that's why we have 3 numbers here. Okay. Next, we have 3 lines, so corresponding to all elements. So here we also adopt the double numbering for element. Okay. Local ID at home and ID of home. So element ID I1 and I2. Okay. And also, so you can see, so we have 2 numbers, and this is a material ID. And so next 8 nodes are local ID of each node for the element. And the last one, so this one underscore is a local ID of the element. Okay, so now it's local ID of the element, like this way. For example, in the case of PC.0, so it's simple. All the elements are coming from this partition. So therefore, so this is local number. And so second ID is all 0. And the material is 1. And so you can see the connectivity for local node. The interesting is this one. Okay, so first element is actually this third one in this process 0. Therefore, the local ID of this element is 3, and the home PE is 0. Okay, and so second one is actually a first element in this partition. So therefore, 1 and 2, and so this one. Okay. So you can see. So and the last one, last line shows a list of local elements. Okay. And so we have 3 components here. So that's corresponding to we have 3 here. And in this case, this is 2. Okay. And so in this case, all 3 elements are local elements, home elements. And in this case, only number 2 and number 3 are this local numbering in the home element. Okay, so but actually, so we use this local element ID and not this double numbering. Okay, so next one is a communication table. And so yeah, it's very simple in the case of this case because we have only one neighbor. Okay. And so this is a communication table which I have already mentioned. And so I don't get into detail because I have already mentioned several times today. And it's a communication table for sending. And so this is a sending part. So sending part is latter. Okay. And the first line shows export index because we have only one neighbors. So we have 4 boundary nodes. Okay. Yeah, like this way. Okay. So if you see this. This is 3, 6, 9, 12. So local number. So there's a so boundary nodes. And in this case, 1, 4, 7, 10 are the export items, so boundary nodes. Okay, so this is how we utilize this so for the sending. And the next one is the receiving part. Okay, so receiving part is so import items and so receiving part and external node. Okay, and you can see so this is a number of the external nodes. So we have a 13 to 16 for both cases. Yeah, you can see. So this 3, 6, 9, 12 is sent to 13, 14, 15, 16. Okay. But please make sure this sequence is identical. Okay. So because of this one and this one, number 3 here and number 13 here is so they are the same node. So therefore, they have to be so relationship face to face like this way. And this is also the case. So this is how the receiving is working. Okay, so because this is a very simple case, and I'll show you a little bit more complicated case using this so 2D case. Okay. So this is a sending part, and this is a receiving part. Okay, for example, in this case, let's think about this number 2. Okay, so we have a number 2, and we have two neighbor processes. So they are number 3 and number 0. Okay, like this way. Okay, and 9p dot is 2, and 9p0 is 3, and 9p1 is 0. So next, we think about this export index, and so yeah, this one. Okay. And totally, we have 2 boundary nodes sent to the process 3, and also 3 are sent to the process 0. So that's why second value is 5. And you can see totally we have 5 boundary nodes. And the first and second are 1 and 4 here. And the third to fifth are 4, 5, 6, like this way. So therefore, so export index 2 is so 2 plus 3 is equal to 5. And the export items are 1, 4, 5, 6. Okay. And this number 4 node is sent to solve the number 0 and number 3. Okay, so this is a external node. Okay, so you can see this, this figure. Okay, so in this case, we have so 3 nodes from process 3, and also 3 nodes from process 0. Okay, so that means so import index is 1 is 3, and the import index 2 is 3 plus 3 equal to 6. Okay. And the import item is in this sequence. First 3 are 7, 8, 10. And the next 3 are 9, 11, 12. Okay, like this way. So in this case, so you can see, so they are not continuous in this so neighbors, but so that will be modified in the actual code. So yeah, this is one example. Okay. So any questions at this part? Okay, so let's go back to this so simple model, and finally, so we should think about a node group, okay, and how the node groups are configured. Okay, and you can see, so we have 4 groups in the original case, and so we have 4 groups in the parallel case. And so they show the numbers, local IDs, including the external nodes. Okay, but you can see, so in the case that this one, there are no nodes which belongs to X minimum. So because of these 4 nodes are just belonging to the X minimum. Therefore, there are no nodes. But in this case, we still keep the 4 groups. And you can see, so 0 means we have no nodes in the first group for X min. And you can see you have no list here. So that means we have no nodes in the X min. So we have a group exists, but so there are no data inside that. Okay, so this is the end of the data structure part. And so any questions for this part? Okay, so if not, so yeah, please do some exercises. So if you didn't have enough time for that. And tomorrow, we start from the main part of the 3D program. But actually, there are very few differences compared to the serial case. And also the linear solver part is the same as the 1D case. And so we have 100 pages of the materials, but actually not so many things to talk. But I will briefly overview that part. And we have a parallel visualization. And after that, so we do some hybrid parallel programming with OpenMP and MPI. Yeah, hopefully, so we don't take so much time. So not at 5 o'clock tomorrow, and so because tomorrow is Friday, and so maybe you want to go home earlier. So yeah, I try to finish so around 3 o'clock or something. Okay. Okay. So any questions or problems? Okay. Okay, thank you very much. And so, yeah, I stay here so until 5 o'clock. And so, anyway, see you tomorrow.